Hey guys, today we're going to talk about function notation. Now recall from our previous lesson that a function is a set of ordered pairs x and y, so that each x component, the first component, is paired with exactly one second component, the y component. Now today we're just going to get a new way to write that y, where y is going to be represented no longer as y, but it's going to be represented as f of x. And this is considered function notation. Now keep in mind, the x is still the independent variable, and now f of x is our dependent variable. Let's jump in to take a look a little bit deeper at this function notation. Function notation was named after a man named Leonhard Euler, a Swiss mathematician who developed it in the 18th century. And f of x is simply read as f of x. So for example, where we used to see y equals 2x plus 3, now we'll see f of x equals 2x plus 3. X is considered the argument of this function. So if I replace x with 1, I'll replace 1 every time I see an x in the equation. So now f of 1 becomes 2 times 1 plus 3, which is 5. Another form of notation that we're going to see in this unit is called mapping notation. And it's written just a little bit differently with a colon, an x, and an arrow, and then the equation follows. So f colon x arrow 2x plus 3 simply means if I let x be 1, it is now going to map 1 onto the equation 2 times 1 plus 3, which is 5. And that is known as the result of the function. Let's take a look at a few more examples. In example 1, we're given this temperature function where I substitute the value of the Fahrenheit to find the value of the degrees in Celsius. So here it asks me to evaluate T of 86 degrees Fahrenheit. I'll substitute the argument 86 into the equation, and this will result in 5/9 of 86 minus 32, which gives us 54, and 5/9 of 54 will result in 5 times 54, divide by 9, and that translates to 30 degrees Celsius. So when it's 86 degrees Fahrenheit, it's 30 degrees Celsius. All right, here's another example. We're given the function notation g of x, which it's okay to replace those different letters. G of x equals 3x squared minus 5. Let's evaluate g of 7. So the argument g of 7 means we'll square 7, multiply it by 3, which results in 147, and then we'll take away 5, and our result will be 142. Okay. Let's take a look at a few more examples. Here's one with mapping notation. So we see we're going to take x and we're going to map it onto x plus x squared divided by 20. So to evaluate f of 10, we have 10 plus 10 squared divided by 20. We'll square our 10 first to get 100. 100 divided by 20 comes next in our order of operations. So that results in 5. Finally, 10 plus 5 is 15. So 10 is mapped onto 15 in that mapping notation. All right, our next part of this asks us to evaluate f of s plus f of 10. So now I'm just going to substitute s in wherever I saw x, and since I know f of 10 is 15, it results in s plus s squared over 20 plus 15. All right, a couple more examples now. We're given a function notation and asked to translate this to mapping notation. So remember, our two variables here are h. We'll start off with the h, colon, and it's going to take all of our x values and map it onto 3 times x plus 5, all under the square root symbol. So let's evaluate 8. 8 will now be mapped onto 3 times the quantity of 8, or 3 times 8 plus 5, and then all of that falls under the square root. So that's the square root of 24 plus 5, resulting in the square root of 29. All right, and our final example now, we're going to take a look at mapping notation and be asked to write this in function notation. So function notation, in our mind, always starts off with f of x. However, if we look at our mapping notation, we don't have an f or an x. We actually have an r and a c. So we'll write this as r of c. C is our argument or our independent variable, and r is our dependent variable. And we'll get r of c equals 2 times c plus 10 divided by c.